So it's my pleasure to be here tonight to talk about solar fireworks. It's quite apt with the weather outside, but thank you all for making the journey. And I'm going to show you some beautiful observations we have of the sun. I am very much a sun enthusiast, but observations we have for looking at the most energetic events that happen in our closest star. So I will just begin by showing you this movie, right? So this is just to give you context. This is not a simulation. These are observations of the sun taken in extreme ultraviolet wavelengths or emission, right? So when you think of UV, we hear, UV rays, that they impact our skin, but most of these are actually absorbed in the Earth's atmosphere. So when we go to space, we can actually look with a telescope at extreme ultraviolet radiation from the sun, and we can see it's really, really quite dynamic. This is taken by NASA's Solar Dynamics Observatory of one of these solar eruptive events, or solar storm, or what I'm calling solar fireworks. Just to give you a scale about how large these actually are, and think about this throughout the whole talk of how big the sun actually is. This is the Earth to scale, right? This is obviously not where the Earth is, but this is just to give you an idea. You're going to see lots of movies of things erupting, but the Earth is absolutely tiny in compared to these huge solar eruptions, right? So when we think about our closest star, it often seems like this yellow ball in the sky that sometimes we see in Ireland, but it's really quite a dynamic, magnetically active star, and that's what I'm going to talk a bit about today. So this is an actual observation over the past few days taken with that same NASA Solar Dynamics Observatory. And this is looking at a wavelength in visible light. So if we had a telescope on Earth and the sun was shining, and we put a solar filter on it, we would see something like this. This is the surface of the sun, or what we call the photosphere of the sun. And it looks kind of boring, right? If you were a sun enthusiast and this is all you saw, I don't know why you would be a sun enthusiast. But the surface of the sun is around 5,000 degrees, which is really hot, right? But it's actually, if we kind of stop this and we kind of look at one of these regions, these are called sunspots. And these are dark regions on the sun where the magnetic field in the solar atmosphere of the sun, and at this part, is so strong that it actually inhibits convection. So can't actually see, it's actually slightly cooler, and that's why it looks dark. And I'm going to show you a movie now of this is the Japanese Space Agency's Hinode mission. It's a little bit hard to see on the screen, but if we zoom in, we can actually see that the sun is actually like a bubbling pot of molten lava, right? This is called convection, and these are called granulation cells on the surface of the sun, where hot plasma, which is a really, really ionized gas, is bubbling up underneath the surface. So even when we think the sun is boring, when you zoom in with really high-resolution telescopes, it's really quite interesting. Now, if we look at the magnetic field measurements of the sun, so looking at how strong the magnetic field is on the sun, this is an image of what we have. So this is, again, an observation from this morning, so from 9 o'clock this morning. We've downlinked data regularly, and I just took this one from making this talk at 9 o'clock this morning. And this is measuring the magnetic field of the sun, right? So you can see, if you remember where that black sunspot was, we can see it's quite complicated. The white color is basically positive magnetic field, so magnetic field coming out of the sun, and black is when it's going in. And what we can use is this magnetic field map of the sun to extrapolate out what the magnetic field of the sun might look like. And this is what it would look like today. So as you can see, it's a hairy spaghetti ball, as we would expect. But really, the blue and the red are kind of these open magnetic field lines of opposite polarity, like a dipole, like think of a magnet. But you can see that there's all this kind of wiggles and kind of spaghetti loops. And that's the magnetic field of the sun being quite complex, which we're going to come back to. And this graphic kind of shows, this is a nice visualization. If we imagine these white lines being the sun's magnetic field, it's continuously evolving. And we actually have a stream of particles that are emitting from the sun continuously. This is known as the solar wind. If we go back to the magnetic field measurements of the sun, this again is the surface of the sun, 5,000 degrees. Where it starts to get interesting is when we start to look in the atmosphere of the sun. And if we look at this is looking again at extreme ultraviolet light, so really high energy light. So if you go to space and you put a filter on your telescope and you look at this wavelength of the sun, this is moving outwards from the sun. This is called the chromosphere. And what's weird is that the temperature of the sun starts to increase, right? So we went from 5,000 degrees to 50,000 degrees. That's like walking away from a fire and it starts to get hotter. And you can see, if we think back to where those magnetic field structures were, or the sunspots, that's where we have bright regions. These are called active regions. Now, if we look at a different wavelength or a different color of light, looking at a different energy, this is looking at 171 angstrom, again, extreme ultraviolet. We're moving again further out into the atmosphere of the sun, or the corona, and we start to get even hotter. We're going up to 1,000,000 degrees. And you can start to see these kind of loop structures, right? These is magnetic fields penetrating out from the surface of the sun, which is holding hot plasma in it, and that's why it's bright in extreme ultraviolet light. I'll also just note, if we go, this is again, sorry, zoom in just to show you how different it is to those convection cells we saw. At the surface of the sun, in the atmosphere, it's very much quite dynamic. And again, we can look at a different color and we see again, we're going even hotter, 5 to 10 million degrees. That's one of the biggest challenges we have in solar physics and in stellar astronomy. Why is the solar atmosphere hotter than the surface of the sun? We do not know that. That is the coronal heating problem, and we don't know how the energy is transported. It's not what I'm going to talk a bit about today, but just remember that. If you don't remember anything else, that's a really cool thing. If you solve that, you win a Nobel Prize. So just to show you that the sun, even when we think it's boring, when we look invisible light and we get a telescope and look at it, this is the past few days of observations in different energies. We can see the sun is really, really quite dynamic. And even when you start to look at the sun, for as much as I look at the sun every day, you start to see patterns in the sun. And if I just pause it here and look at this, it's very apt for Halloween. I don't know if anybody else can see this scary face with the two active regions and a little nose. And this is kind of like a little smile. And what this structure is here, this is what people call it, a coronal hole. You see sometimes in the news a hole in the sun. What this actually is the magnetic field's open and it's actually blowing away some of the plasma of the sun, so it looks a little bit darker in this wavelength. But there's nothing to worry about. They're well known, these coronal holes. Now, all of the sun's activity in the solar atmosphere is driven by its magnetic field. And we have to remember that the sun is not solid like Earth, right? So it rotates differentially, meaning that different parts of the sun rotate at different speeds. And what this actually ends up happening and why it becomes a big spaghetti ball when we look at the magnetic field, if you think of a dipole like Earth, right, then all of a sudden you start getting over years, you have this kind of complex magnetic field structure. So the plasma moves, it carries the magnetic field with it, and it starts to get very, very complex. So the sun goes through these cycles of being kind of like a dipole, open magnetic field, to being a hairy spaghetti, to being goes flips, and it goes back to being a dipole. And how we can measure this activity as a function of time is by looking at sunspots. As I said, these sunspots are really high regions of intense magnetic fields. And we've been looking at the sun of these sunspots for hundreds and hundreds of years. This is a drawing that someone did in the 1600s, tracking sunspots as a function of time. And we've been able to continuously do this, and we can do this now with modern telescopes. We can see these sunspots. And some of these detailed drawings from 1600s were almost as good as what we kind of get today with some of the resolution telescopes. And then what we can do is we can track these sunspot numbers and count them as a function of time. And we start to see we have a solar cycle. This is plotting here the sunspot numbers, so the number of sunspots on the sun as a function of time. So you can see every 11 years it goes through periods of being really high, lots of sunspots on the sun, it's very active, being very quiet, and there's nothing really going on in the sun. And this is when the sun goes from being straight to very, very spaghetti-like to back being straight again. As you can see, some are larger than others, and we're currently in a solar maximum. So the sun is very active at the moment. This week it hasn't been that active, which is annoying because I'm currently using a mission to look at the sun, but so these flares. But anyway, it's typically quite high at the moment. And to show you what this might look like, if we compare what those EUV extreme ultraviolet images look at solar minimum compared to solar maximum, they're two very, very different stars. Now, I want to talk again about these solar fireworks, these solar eruptions. And this is a movie that's going to show you, again, one of these large solar eruptive events. Again, think back to the scale about how small the sun is. So this is, again, looking at NASA's Solar Dynamics Observatory. This is a very large eruption that occurred just away from the sun, or to the left-hand side of the sun. What we're going to do is we're going to zoom out and use European Space Agency's SOHO mission, which blocks out the main portion of the sun, to see kind of faint eruptions around the surface. When we combine these together, we can really see the scale of how large these solar eruptive events actually are. So again, to give you context, this is not an alien, this is Venus. But Venus is very bright. It's actually saturating our pixels, and that's our detector, and that's why it looks like it is a tiny. But again, if we kind of play that quickly through, if you were a planet in the path of one of these solar eruptions, just think about how grand scale these are. This is magnetic field and plasma being emitted away from the sun at hundreds of kilometers in a second of energies we can't even compare to what we have on Earth. Luckily, this one was not going towards the Earth. But how do these work? How do we understand these solar eruptions? And it all goes back to the solar magnetic field. If you think of, again, the magnetic field being like elastic bands, and what happens is as the sun is kind of moving in different speeds at different parts of the sun, the magnetic field starts to get twisted. And if you start twisting and twisting and twisting an elastic band, you start to build up potential energy. And eventually what's going to happen is that the elastic band is going to snap. And this is what we have a thing called magnetic reconnection, where the plasma and the magnetic field reconnect together and release all of this stored energy. This is a very simplified cartoon to show you this, but it actually really fits with what we actually observe. This is an observation of a solar flare, one of these, results of this magnetic reconnection. So this is again extreme ultraviolet light, looking at around 1 million degrees Celsius. And a solar flare, we usually classify it by looking at X-rays. So Donna mentioned X-rays. These are really, really high energy photons that occur from the sun. And we measure a solar flare but based on the total X-ray flux we see from the sun. Usually the sun doesn't emit too many X-rays. If it's very quiet, we don't really see too many. They're very kind of low down here. But in the matter of tens of minutes, we have several orders of magnitude. So this is again 10 times greater, 100 times greater, 1,000 times greater. Total flux of X-rays from the sun increase over a matter of minutes. And this is what we call a solar flare. And just to give you context, if an eruption happens and a plasma gets emitted from the sun, it takes some time to get here. It could take a day, it could take 2 days. But when we have photons, so this is light from the sun, X-rays, it gets to us in 8 minutes. So really, once we see it at Earth, basically it's already happened. And this is what we call a solar flare. And we classify these flares basically on how bright this gets. So if it goes above 10 to the minus 5 watts per meter squared, it's an M-class flare. Above 10 to the 4, it's an X-class flare. So we're going to talk about space weather events. It's M and X-class flares. These are the large ones that actually have an impact on Earth. And often when you have a flare, you also have this kind of eruption that goes with it. And this is what we call a coronal mass ejection. So a flare and a coronal mass ejection. The flare is the light, and the coronal mass ejection is the ejection of material, and both have an impact here on Earth. Now, large events happen kind of not that frequently, right? They're rare. They're hurricanes of our weather. They don't happen all the time. But the sun is always flaring. And this is a movie that I made showing observations from Solar Orbiter, which I'll talk a little bit about later, which is a European Space Agency mission that is going in and out to the sun, really, really close in and coming back out to Earth. And each blue dot in this is a solar flare. So this is just over kind of a period of time, just to show you how often the sun is flaring. The sun is flaring all the time. It flared today. Hopefully it will flare again tomorrow, because I'm using these observations at the moment. But basically, each size of this dot is basically how large this flare is. So I guess the takeaway is that the sun is really active and it is flaring all the time. It is always showing these solar fireworks. And usually when we talk about space weather, which I'm going to talk about now, it's really only these large, really, really large events that we care about. But from a physics point of view, we really care about these small ones too. And given that it's Sound of Science, I thought I'd bring us back to 2003. This was the Halloween solar fireworks. So these were two of the largest flares that we've observed in kind of modern times. So this is again those X-ray observations. So we see these extreme peaks. So this is X17 and X10. To give you context, we haven't really had flares that big in the past 20 years. So these were 1 in 20-year events. And this movie in the background is showing a sequence of days of these storms. So again, this is using European Space Agency's SOHO mission to block out most of the light to see these eruptions that go on. And if we look over the several days, we can see the sun is continuously erupting. You'll see in a minute, very large eruption. And all of these speckles are actually energetic particles from the sun that hit the detector and basically blind it. So the fact it looked like it was blowing out in one big thing means that it was actually coming towards us. These Halloween storms caused significant impacts. There was power outages in Sweden. It caused significant impacts to transformers in South Africa. Air flights were actually rerouted. I mean, it was one of these extreme cases that really kind of shook the world about how susceptible we are to the sun. So what is the reality of living with an active star, right? I've shown you all these nice movies of these eruptions. And this is an infographic, a really nice cartoon, obviously not to scale, of the sun showing one of these very large coronal mass ejections, these solar fireworks. And this is us here on Earth. Now, luckily for us on Earth, we have a lovely magnetic field and an atmosphere. And that protects us from all of these solar storms. And this is a simulation just showing the Earth's magnetosphere, as you can see, the magnetic field of the Earth, as one of these solar storms passes us, right? So this is, again, the Earth. We'll see here, as the solar storms pass, it really compresses our magnetic field, our magnetosphere, and really disrupts our magnetic field. And it can also disrupt our atmosphere of the Earth. And this can happen for several days, right? So as these things are blowing by, it has a significant impact on our Earth's magnetic field. So it's great for us humans on Earth, that protects us, all good. But what we're going to see is if you have a technology, if you're flying in this magnetic field, use anything that depends on the magnetic field, and most of our technological infrastructure does, it can be a significant concern, let's say. But key thing to remember, we have magnetic fields, it's all grand. And this is just a context as well, we think of us and the sun in space, but we live in a solar system, and the sun does not only just have influences about us here on Earth. This is again a simulation showing these large eruptions from the sun and how far out into the heliosphere, into our solar system, these things actually travel. So we can detect solar eruptions and the solar wind out past many planets, even out to Jupiter. So I guess, it's interesting to see how this evolves. It shapes our whole heliosphere, but also gives us thinking about, if we're going to go to space, we're going to travel to Mars. We do not have a magnetosphere, do not have magnetic fields, and we need to think about traveling through unprotected in our solar system as humans. This is something that people are really considering now, that we're going back to the moon and we're going back to Mars. We need to understand how and when the sun is going to impact space travel. Now, one of the beautiful things these solar eruptive events actually have for us here on Earth are the aurora borealis, or the northern lights. And this has been a connection for many, many years that we've known about this. And they've really been, they have inspired generations of people going back hundreds and thousands of years. You hear there is actually writings from early days in Ulster in 700 AD, where people were talking about a spectacular event where the night was shining bright red for several days. At the same time, they used tree ring analysis to show one of the biggest flares that we actually saw in the sun ever occurred around that same time. Now, the sun, as I said, is in solar maximum. So last year we had two very, very big storms. I don't know if anybody saw the aurora. There, you can see them in Dublin. So these are actually the aurora from the May and October storms. So this is down in Cork and Baltimore. So as far south as Cork, we could see emission from the aurora. And this is from Mayo. And then this is from Iceland. So of course, the more far north you go, you think about our magnetic poles, this is where it's impacted, right? So our magnetic field protects us, but do we have parts where, I guess, these energetic particles come down, interact with our Earth's atmosphere, and cause the beautiful aurora borealis? So this is a very, very nice impact of solar storms. But another kind of nice Irish connection is the first person to actually really scientifically connect what was happening on the sun and what was happening in the Earth's magnetic field was an Irishman called Edward Sabine. And he actually, in 1852, he actually commissioned and built, well, earlier than 1852, he built this magnetic observatory in Trinity College, Dublin. It was actually built in the Provost Garden. If any of you Trinity heads are here, you will know this building does not exist anymore. It was actually moved to UCD. It was deconstructed. But Sabine actually was able to show, for the first time, he looked at magnetometer measurements, so measuring the magnetic field of Earth, and found that there was a connection to the solar cycle. So again, it's just kind of nice to see that, when you go back, well, it's always a story, an Irish person did it originally, always, but this is actually a direct connection with an Irish person that was working and looking at the connection between the sun and the Earth's magnetic field. And in the 1850s, there was kind of some other interesting things happening. People were very interested in the sun. It must have been a very active time. And this is something we call the Carrington event. So Richard Carrington was a British astronomer, and he was doing daily sunspot drawings. So as I said, people have been drawing sunspots for hundreds of years. And he noticed, as he was drawing them, really two bright, intense lights as he was drawing it. And he didn't know what it was at the time, but he thought it was very strange. And what they found was 17 hours later, they found a significant disturbance, magnetic disturbance in ground-based magnetometers measuring the magnetic field of Earth. And what we realized today, this was the first direct observation of a solar flare, a solar firework that happened, and direct measurements on Earth. Now, this was so large, we can go back and look at newspapers. And this is a cutout from the Boston Times, I think. And basically it showed that the aurora was so bright that you could read by night. And another thing was there was an extraordinary effect on telegraph wires. So back then, really the only technological infrastructure they had was telegraph wires. And they found that they were actually working without the usual batteries. So something was happening in our Earth's magnetic field to generate currents to actually run telegraph wires and to actually power them. And that was a direct connection with the sun. And there's actually kind of stories of things sparking and people talking to each other between telegraph wires, again, solely done by the kind of events that we've seen on the sun. And there are lots of things that say if this event happened now, it would be a really dramatic impact. It would have a significant impact. It was probably one of the largest events, 1 in 100, 200 year events that have occurred. So if you ever hear again of a story about a solar storm or at another talk, you will definitely hear about the Carrington event. But now we live in a society, as I said, really dependent on technological infrastructure. And this is an infographic for the European Space Agency, which highlights all the different aspects that's susceptible to a solar storm hitting Earth. Of course, if you're in space, you have intense radiation if you're an astronaut. If you are any satellites in space, you can have single event upsets. So you have energetic particles that hit your detectors and cause upsets. It can also impact your drag of your satellites. So satellites might have to be put up to a higher drag or a higher altitude if a solar storm comes. If you are flying a polar flight, you can have intense radiation emissions, so we reroute flights. Significantly, what's important is that it induces currents. So similar to inducing kind of currents in telegraph cables, it can induce currents on our power grids to large enough extents to actually blow transformers. And this is something that people we need to think about. You can't just go and buy 100 new transformers. So at the moment, power grids are kind of one of the biggest clients, I guess, for space weather prediction. And just to kind of give you context, SpaceX launched lots of Starlinks into space, and they launched one relatively recently last year, and a geomagnetic storm actually was occurring at the same time, and they lost 40 out of their 49 launched satellites. And to even bring you home to how real space weather is, it is now actually mentioned in our national risk registry. So each country has a national risk registry to kind of say about what are the risks and what are the impact of them. It's only recently been added to the Irish one. It's been a part of the UK one for a very long time. It was actually on the same scale as a global pandemic. So it's kind of interesting how we understand things now. But basically, if we read what it says in this, space weather, its impact on global connectivity is at risk, in particularly as we approach the solar maximum of 2025. Satellites are vulnerable to its effects and become disabled or damaged. Now, even further than this, Lloyd's of London, which is kind of a big looks at kind of risk and insurance across the world, they did this earlier this year in March, and said a global extreme space weather event, so a very, very large storm, something like that Carrington event, could be a global potential economic loss of $2.4 trillion, right? So we're not just talking about the sun being interesting as a beautiful thing and we can do nice science. It actually has direct impact now from a global economic point of view. If you have a huge solar storm that impacts your power grids across the globe and your satellites, you start to have a very significant geopolitical and pricey problem. So this is one of the other reasons why we want to understand the sun. And just to kind of give you some context here, there is a large space weather operational forecasting network, of course, around the globe. The European Space Agency has a space weather service network that are providing space weather forecasts for those that need them, right? So we don't need a space weather forecast. If you're walking down the street, maybe you'll see the aurora. But if you operate satellites, if you operate power stations, if you operate gas line pipelines or GPS, this is something that you're going to need to be aware of. So it's kind of interesting, there's a whole world of space weather operational forecasting out there. And I think as we kind of move into society becoming more and more dependent on our technology, we're going to hear more and more about space weather. Now, space weather forecasting, as the name would suggest, it's like weather forecasting. We want to forecast when these events are going to occur and how large they're going to be. And in order to do that, we need to understand how they happen, right? We need to understand the physics of what drives them. We're still not in a very good position of forecasting solar flares, right? Maybe when we see what happened, we can say the eruption is going to come in within the day, but we can't say in the next 2 hours it's going to be a large solar flare. We're currently not at that. We're at a stage where weather forecasting was, if you were in New York, you call a guy in Chicago and you'd say, hey, what's the weather like there? And then you predict what it's going to be like in New York. So in order to, I guess, improve space weather forecasting, we need to learn more about the sun. And this is kind of where my research comes in, is using new insights from ESA's solar orbiter mission. So I showed you a very quick movie of going in and out of solar orbiter. This is ESA's flagship solar mission to look at the sun and to understand some of these things about solar fireworks. So it's a mission, solar orbiter, as I mentioned. It was launched in February 2020, and its nominal mission science phase started in November 2021, meaning that its real science operations started in November 2020. Now, what makes it unique is two things. One is that it has 10 different instruments on board. It's looking at the sun and taking amazing images in lots of different light. And it's also measuring what the conditions are at the spacecraft. It's measuring what the magnetic field like is at the spacecraft. It's measuring particles of the spacecraft. And there's no kind of mission to date that's been able to do both of those things at the same time. Furthermore, it's going to try to answer this question: how does the sun create and control the heliosphere? So that's kind of the magnetic activity in the whole solar system. And why does solar activity change with time? So this question is a real science question, but the answers we get from the science question are going to help the solar flare forecasting. And the uniqueness of it, as its name would suggest, is that it's orbiting the sun. But it's orbiting the sun at a very different orbit to Earth. So most things looking at the sun are orbiting the Earth, looking at the sun. So we have the same perspective as what we're doing. The solar orbiter, this is this white line here, over its mission. It basically goes in really, really close to the sun twice a year. It goes inside the orbit of Mercury and follows this kind of elliptical pattern. And it uses Venus to do a series of flybys to get kind of closer to the sun, but secondly, get out of the ecliptic plane. So it's actually going to start to look at the poles of the sun. So when you have the sun in the center, all the planets and everything is orbiting it on kind of a flat disk. So the orbiter is going to get it out of that flat disk and look down for the first time. So it's really exciting and showing some really nice new observations. And I guess the key thing is it's taking the closest ever images of the sun to date. And what does that look like, right? So this is kind of a picture we've seen before. So there are several different missions that look at this light from the sun. But with Solar Orbiter, as we go in really, really close to the sun, when we zoom in, we can actually get down to a pixel scale. So each pixel is, 130 kilometers in this sense. So this is absolutely tiny when you think about the size of the sun. And hopefully it's even not great on this screen. When we look at a part of the sun where we thought nothing was happening, we can see there's all these tiny dynamics going on. There's all of these tiny brightenings and tiny little flares that are happening all of the time. So it seems to be the closest we're getting and the better resolution we have, we're seeing more and more and more things. This is the closest ever image of the sun to date that you've ever seen, that anyone's ever seen. What this allows us to do is to measure energy release on the smallest of scales. And why that's interesting is we want to understand energy release across the whole scales. We want to understand the smallest ones up to the biggest ones, because that kind of trend tells us about how often these very, very large ones are going to happen. And it also tells us about the physics of what's driving them to rate from the smallest little things that happen to the very, very largest ones. And if we zoom in, and this is looking at the pole of the sun, you can see there's continuously little jets happening. So again, if we had our past observations, we would not see anything here. We're seeing continuous streaming and outflows. And this was the first time that these pico flares, the tiniest of flares, were actually helping to drive the solar wind. That's another big question, is what accelerates the solar wind outwards. And it seems that it's actually these tiny, tiny events are actually a huge contributor to the solar wind. Now, as well as these very, very small scales, we can also look at very, very large scales. And as well on Solar Orbiter, we have another telescope that takes a very, very large field of view. So again, that was one telescope that looks really, really close in with high resolution. We have another telescope that looks at a very, very large field of view. And this kind of shows, again, an eruption that we saw in February of 2022. And it was the largest scale we could actually track for a very, very long time. What was also interesting about this is we had another telescope or another spacecraft called Parker Solar Probe, which is a NASA mission, kind of their joint missions. At the same time, it's actually flying through this. So we can measure it from Solar Orbiter and observe it, and we have another spacecraft carrying it through. And we have now, since this nominal science phase that occurred in 2021, we have hundreds of these events that we've been able to observe with a very, very large field of view. So we're starting to be able to track when these are happening. What we're also being able to do is get different perspectives, right? So as I said, Solar Orbiter is going very different to Earth. So it's looking at one side, and then we're looking at the other side from Earth. We can really start to get measurements of how these things are traveling. And again, I showed you kind of movies of very small things happening on the sun in these really high resolution telescopes. But we can also see these eruptions. This is an event from last year. Again, just very high resolution observation of a solar flare. So we're using these scientifically wise to understand how these flows of plasma actually follow on from the magnetic reconnection. How is the energy dissipated from that magnetic energy, from the magnetic field, into the hot plasma that we see, and then how does that propagate out into space? And with Solar Orbiter, we're really able to do that by joining the dots. As I said, it has this uniqueness that it can picture something on the sun, and then it can wait for it to fly by and measure it at the spacecraft. And this is an infographic showing how we can kind of use all the different instruments on board Solar Orbiter together to really join together something that's happening on the sun, and then how that propagates through space. So this is this movie of extreme ultraviolet light. There's a very large flare that happens. It's hard to see here, but there's X-ray observations down here. We can see the tracking of this moving outwards. We have a radio measurement on board, which tracks electrons as they propagate away, and we can measure their speed. And we can actually measure waves that actually hit the spacecraft. Then we can measure X-rays, and we can also see energetic particles. So for the first time, we're really able to see what's happening at the sun and how that moves out into space. And why that's important is to understand the physics of it to be able to forecast it, because we want to understand when these flares are going to occur and how impactful they're going to be. So what's next for Solar Orbiter, right? So I showed you kind of some nice highlights of the science that we're being able to see. But I think some of the next things that are is very, very exciting for it is that we're going to get the first view of the solar poles ever. So we've never been able to see what's going on in the pole of the sun. And that's really important because we don't really know anything about the magnetic field in the pole of the sun. For example, we know the solar cycle is every 11 years, but we don't necessarily know why. We don't know when we're going to have the next largest one. And also we want to understand the whole sun, right? At the moment, usually we only see one side of the sun, but we don't know what's happening on the backside. We don't know what's happening on top. And to get a full view of the sun, to be able to do these predictive models, we need to understand every part of it. So it's really kind of the really unique science is coming over the next few years. So we're in March 2025 now. So this is the first time we've actually been able to measure the pole of the sun a little bit. We're only getting a hint of it. Basically, every kind of year, it's going to fly by Venus. It does use a little gravity assist and gets further and further out of the ecliptic plane. And by July 2029, we're going to be so far out that we will actually have a direct view of the pole. And these are the first hints. So I think this is a movie that will it's not. But yeah, it is. So this is again this magnetic field map of the sun. So we want to measure the magnetic field of the pole. And it's very hard to see, but we're starting to see hints of the pole down here as it moves in, and then it goes up and looks at the top pole. And this is a polar plot. So this little red dot here is actually the center of the pole of the sun. And it's projected into polar view. So the first glances that we're seeing, and this again is only when we're starting to see, this is what we would see from Earth. We looked kind of down at the top of the sun, but from solar orbiter, we're now kind of starting to hint at this. And as we get to 2029, we're going to see more and more of that pole of the sun. So I think it's maybe in a few years' time, somebody else will come back and give a talk and say, we've solved everything. We've seen the poles of the sun. But I think this is really, really, really interesting because there is still a huge amount we do not know about our closest star. It is it is the most observed astronomical object. We have literally hundreds of things looking at it. And yes, I think it's probably the one where we have the biggest open questions. It's almost that we have too much data that it's constraining our models too much, but there are still hugely open questions. However, it's a very exciting time. I think I'm not biased by saying that because I'm a solar physicist, but we are now in an era where we have a golden age of solar physics. So this is just showing you kind of a schematic showing, this is the sun. We have the Solar Dynamics Observatory. I've shown you many movies. We have SOHO, which looks at many things, but it shows the coronagraphs, the very kind of extended view of the solar atmosphere. We have NASA's Parker Solar Probe. So this is actually going in closer to the sun than Solar Orbiter, but it's not taking images. So I was not wrong in saying closest images today. We have ESA's Solar Orbiter, which again is now only kind of starting in this extended phase to look at the poles. We have lots of different missions that are at different planets around in our solar system, which we can also use to measure what the conditions of the heliosphere are at them. We have ground-based telescopes. So this is an observation from DIAS, which is the best solar telescope ever in Hawaii. It's extremely high resolution observations. So this is kind of an observation of, again, looking at the granulation pattern of the sun. We have LOFAR radio telescopes. This is a picture of the radio telescope in Burr. This is part of a larger radio telescope network across Europe. So we're really in a position where we can look at the sun from a huge amount of different angles, both physically and also spectrally. We can really see the sun from radio waves, through infrared, through visible light, to extreme ultraviolet, to X-rays, and even to gamma rays. So we're really seeing this full spectrum. And I think over the next few years, we're going to learn an awful lot more about solar flares. We're going to get an awful lot better about solar flare forecasting. We're going to learn a lot more about our sun as we go forward. So I'm just going to summarize kind of the things I showed you today and some takeaways. So the sun is a very interesting astrophysical object. People are always interested in black holes or extragalactic things. I know I'm massively biased, but the sun is our very closest star. That, we have this astrophysical object that we can do resolution observations of 100 kilometers. You just can't get that in any other astrophysical object. It also gives us a laboratory for doing plasma physics, extreme conditions of magnetic field and hot plasma, which we can actually observe directly. Solar flares are stars' fireworks, so all to do with the magnetic field on the sun and how that impulses outwards. I didn't mention it, but other stars also have stellar flares, right? So we can also use our sun as kind of analogy to how other stars are going to behave. These storms of these flares shape the weather in space, so the conditions in the kind of magnetic environment of the Earth and beyond. We're watching the sun up close, right? So at DIAS, we are kind of leading different things about Solar Orbiter. Ireland has had a very long tradition with Solar Orbiter. It actually, NBio is an Irish company that developed the heat shield for Solar Orbiter, right? So Ireland is playing a huge role in the European Space Agency and with missions like Solar Orbiter, and at DIAS we're leading a lot of that science. I think it's kind of nice that Ireland does have a long history of space weather and solar physics. We think back from Trinity's 19th century magnetic observatory to now a magnetic network that we run at DIAS called MAGI, from kind of new missions like Solar Orbiter and other ones we're doing. And we're all doing this from Dunsink Observatory. So this is the DIAS building Dunsink Observatory, which is out in Ashdown, where most of our astrophysics division works. So I think it's quite nice that, in this old building that was built in the 1780s, we're now doing kind of next generation science from our computers and looking at the sun. So with that, I will finish on my current observation, which we took only a few weeks ago, of a solar flare with solar orbiter. It's my new current favorite flare. So thanks very much, and I'm happy to take any questions.